Linear approximation. In this video, you will learn how you can approximate functions locally by linear functions. Linear approximation is an excellent method to estimate f of x values because linear functions are the easiest functions with which to work. So they provide a useful tool for approximating function values. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. The given figure below shows a curve y equals f of x. Let's find the derivative at x equals a. We know that the slope of the tangent that is drawn to a curve y equals f of x at x equals a is its derivative at that point. That is, the slope of the tangent line is f prime of a. We can rewrite the equation above to obtain the equation of the tangent line. At x equals a, the slope of the curve and the slope of the tangent line are f prime of a. In fact, by zooming in toward x equals a, we should notice that the graph looks more and more like its tangent line. In other words, for a brief moment, the function f of x is linear and stays near its tangent line, and we use the tangent line at x equals a as an approximation to the curve when x is near a. I denote a capital Y for the tangent line and a small y for the curve. Consider a function y equals f of x that is differentiable at a point x equals a. The linear approximation or the linearization of f of x at a of f of x at x equals a is given by the equation. Let's see how it works. Find the linearization of the natural logarithm at x equals 1 and estimate the value of ln of 1.02. Find the percentage error if the actual value of ln of 1.02 is 0.0198. There are three easy steps on how to perform linear approximation. First, plug in the given value of the given variable a for x, then solve for the value of y. Second, take the derivative of the given function f of x and its value at point x equals a to find the slope of the tangent line. Third, plug these values into the linearization equation above. It's done. To solve item B, we replace x with 1.02. Pay attention. To solve item C, we use the formula as follows. We subtract the approximate value from the exact value. Then we divide the result by the exact value. To find the percentage error, multiply the result by 100. The percentage error was about 1%. Let's see the next example. Use the linear approximation formula to find the approximate value of these square roots. We know that 3.92 and 4.2 are very close to 4. We know the value of square root of 4 is 2. We also know that the linear approximation formula is a function that is used to approximate the value of a function at the nearest values of a fixed value. So the suitable function we are dealing with is the root of x. We now follow the steps to perform linear approximation. First, plug in the given value of the given variable a for x. Then solve for the value of y. Second, take the derivative of the given function f of x and its value at point x equals 4 to find the slope of the tangent line. Third, plug these values into the linearization equation above. To find the square root of 3.92, we replace x with 3.92. And to find the square root of 4.2, we replace x with 4.2. Let's see the next example. To solve this example, first of all, let's convert 20 degrees to radians. The function we are dealing with is the sine of x. We are asked to determine the linear approximation for sine of x at x equals 0. So, because x is small, we know that x is close to 0, and we can pick a equals 0. We now follow the steps to perform linear approximation. So, as long as x stays small, we can say that sine of x is x. So, the first statement is true. Let us find the error. Let's consider the exact value of sine of 0.349. The sine of 0.349 is 0.342. The percent error is approximately 2.02%. So the second statement is true. Pay attention in the next example. This is actually a somewhat important linear approximation used fairly heavily in physics and mathematics. You should try to solve it yourself and then check the answer.